Hi everybody, this is Dr. Vahid Aryadustir. In this video, I'm going to demonstrate how to do a factor analysis and a principal component analysis in SPSS. This is the data that I'm going to use, and the data has been chosen from the book by Salkin and Frey, Statistics for People Who Think They Hate Statistics, a very interesting name. I would also like to add that if you're interested to learn more about statistical analysis, this is a book that we published recently, Quantitative Data Analysis for Language Assessment, Volume 1. If you go to the last chapter of this first volume by Limei Zhang and Wenshu Luo, you'll see that they have discussed the application of factor analysis and also principal component analysis in details. So let's go back to this questionnaire and see what we can get out of it. So as you see, we have 23 items here, and we want to cluster them into separate factors. One of the first things that we need to do is to make sure that the data is normally distributed. I have discussed that in details in several other videos, so I'm not going to go through that for this presentation. For data analysis, I'll only use the first 10 items because this is only a demonstration. So we need to go to Analyze. Under the Analyze menu, you should choose Dimension Reduction and then choose Factor. I've already done this, so I'm going to reset and choose item 1 all the way to item number 10. I suppose there are 10 items. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 items. Right, so I will go through each of these tabs and explain what the options are and what they mean. First of all, descriptives. For descriptives, I suggest that you include initial rotation solution, and for correlation metrics, include coefficients, significant levels if you like to, because they will show you if the correlations are significant or not. So let's choose it. There's an index called determinant, and I'll show you later. It's important for us to estimate that, and also KMO and Bartlett's test of sphericity. The rest are not necessary. Continue. Then for extraction, as you see, there are under methods, there is a drop-down menu in which there are different methods of factor analysis or factor extraction. Generally speaking, in our fields like applied linguistics, second language acquisition, or language assessment, or psychology and social sciences in general, scholars usually differentiate between principal component analysis and factor analysis. SPSS labels factor analysis as principal axis factoring. The difference between these two is that in principal component analysis, you assume that the total variance in your data equals the common variance between your items. On the other hand, in principal axis factoring, the assumption is that the total variance in the data equals two things. One is a common variance, pretty much like in principal component analysis, plus unique variance. So unique variance does not exist under principal component analysis. The unique variance in factor analysis can be further divided into specific and error variance. So let's choose principal component analysis, or PCA, for the first round of analysis. I would also like to get Scree plots, and I'll explain what Scree plots are later. In order to analyze the data, you can either use a correlation matrix or covariance. I assume correlation matrix is better because it's standardized. At least you can make sense of the data more easily. It's more intuitive. Based on eigenvalues, you can extract the data, or you can specify the number of factors that you want to extract. It's a good idea to extract based on eigenvalues first. And I'll explain what eigenvalues are when we look at the output. Eigenvalues greater than 1 are frequently used as a criterion to extract factors. Finally, maximum iterations of convergence is by default 25. If you think that your data is small, for example, if you have a sample size smaller than 300, I would suggest that you increase the number of iterations to 50 or even to 75, in some cases even 100, because with smaller samples, the convergence becomes increasingly more difficult. Of course, if your data converges late, that could be a little bit of a red flag. So continue. Then for rotations. As you see, there are different methods of rotation. So rotation is a technique, something like a geometric technique that helps you make your factor solutions more interpretable and meaningful. There are overall there are two types of rotations. So let me just draw this for you. One type, which is represented by direct oblique and promex here, is known as oblique rotation. In oblique rotation, you assume that the factors or the components that will emerge are related, or they have some sort of correlation with each other. On the other hand, there is orthogonal rotation, which includes varimax, quartimax, and equimax in SPSS. And it assumes that basically there is no correlation between the factors or the components that will emerge in the analysis. In social sciences, generally speaking, in psychology, in language learning, etc., the assumption is that the factors are typically correlated with each other. Therefore, I suggest that you choose direct oblique or promex. So let me go through these quickly and tell you what each of them means and how you can use it. For the first one, which is Variance method, which is an orthogonal rotation method, you can use this to minimize the number of variables that have high loadings on each factor. So this method therefore simplifies the interpretations of the factors. For the direct oblique, which is an oblique method of rotation, as you see, you have a delta score. If I choose it, you have a delta of 0 here, which is the default. If you have delta of 0, the solutions, that's the factors that will emerge in this analysis, will be most oblique or highly correlated. So you can actually change this. For example, you can choose a negative value and the factors become less oblique, or you can choose something greater than 0, for example, anything equal to or less than 0.8 to override this default value. I'm going to leave it as 0 actually, because I assume that my factors are going to be highly correlated. Now, if you want to choose a quartimax method, you will change those assumptions. By choosing quartimax, you minimize the number of factors needed to explain each variable. So this method simplifies the interpretation of the observed variables. Equimax is basically something like a combination of quartimax and varimax. So it's a rotation which simplifies the factors because it's based upon varimax, and also simplifies the variables because it's also based upon quartimax. In other words, the number of variables that load highly on a factor and the number of factors needed to explain the variable are minimized in this solution. And finally, promex, which is another oblique rotation, which assumes that factors are correlated. This rotation can be calculated more quickly, and therefore that's one of the advantages of using promex, especially if you have a large sample size. I would suggest that you use promex. For this analysis, I use direct oblique, and I assume that is pretty common in different fields. We would like to display rotated solutions, and again, if you would like to change the maximum iteration or convergence, you can change it to anything more than 25. Click continue. For scores, if you're interested, you can save the scores of each participant on every factor or every component. They will be saved as separate variables in the datasheet later. So I'm not going to do that because I don't need this for the time being. And for options, you can leave missing values as is because you don't have any missing values. But for coefficient display format, I would suggest that you sort by size, because otherwise it gets quite messy. And also suppress, you can also suppress small coefficients, anything that's, for example, smaller than 0.03 could be suppressed. And that's because really you want to have a tidy and neat kind of metrics. Okay, although I did this, I'm going to unclick them because I wanted to show you how this can be done. I'm going to unclick them because I want to show you how to calculate eigenvalues, and therefore I'll need all the statistics without suppressing anything. I think that will be useful. So let's click on continue. I have now chosen 10 items and gone through these tabs. I'm going to click OK. Okay, so for correlation metrics, which is the first output of the analysis, you can go through the correlation statistics and find out if there is any low correlation. For example, this one is pretty low. This one is also low, minus 0.074. If anything is smaller than 0.3, keep an eye on it. Actually, quite a few of them are. But interestingly, all of these correlation statistics, almost all, with this exception, are statistically significant. So it indicates that our correlation matrix is more or less fine in terms of the lower boundary, but the higher boundaries should also be taken into account because we want to avoid the problem of multicollinearity. Multicollinearity arises when you have correlation statistics larger than 0.8. In this case, I don't think we have any, luckily for us. Yeah, this is the diagonal, and below the diagonal, just by eyeballing, I can't see anything. And these are p-values, as I mentioned before. So it seems that overall, our correlation matrix is not too bad, and especially if you look at the determinant value here, right at the bottom, if it's larger than 0.00001, that's 4 zeros. So if it's larger than that, then your correlations, which were shown here, are pretty fine and they can be used in factor analysis. This is basically the first piece of evidence that we can run factor analysis on our data. The second piece of evidence comes from the Kaiser-Meyer-Olkin measure of sampling adequacy. If this statistic, as you see here, or KMO for short, is larger than 0.5, it means that there is enough variance in the data that can be partitioned using factor analysis. In other words, the data is scalable or can be submitted to factor analysis. Bartlett's test of sphericity is also telling us a similar story. It means that the items have a good correlation with each other, and the variance can be partitioned. We need a sig or p-value smaller than 0.05, and in this case, it's much smaller than that value, as you see. It's very small, actually. It's almost zero. Yes, it's basically zero. So now this is the second piece of evidence that our data can be submitted to factor analysis, or in this case, of course, principal component analysis. Now we have communalities. Communalities is also a very useful statistics here. Communalities, I should say. That's the correct pronunciation. And communalities refer to the correlation of it's like a relationship between the item and the components that emerged in the analysis. So it's analogous to what we call coefficient of determination in correlation analysis, and that's R square, or R square in regression analysis. That's the amount of variance explained. So if you have a small amount of communalities, anything below 0.3 or so, that item could be a little bit of a red flag, and it may not load on any of your factors. In this case, every statistic that you see under this extraction column is fine and is above 0.3, which is good. In principal component analysis, as I said, the total variance is equal to common variance. So the total variance, which is extracted in the initial round of analysis, is always set at 1. So we have to always look at the extraction or the second column of communalities to figure out whether items are functioning properly. So this is the third piece of evidence for us that factor analysis can be done on our items. Next is our total variance explained, and this is an important table for us. In this table, we see initial eigenvalues, and eigenvalue is an important statistic, and it refers to sum of squared component loadings or factor loadings across all items for each factor. So I say that again, is sum of squared factor or component loadings across all items for each square. Now that might sound like a little bit of a difficult concept to understand. Actually, we can estimate these eigenvalues manually, so that will help us understand them better. So let's just keep these statistics in mind and go quickly down to component metrics and see how we can investigate how we can estimate eigenvalues. Like I said, eigenvalues are the sum of squared factor loadings, and these are factor loadings, unrotated factor loadings on each of the three components. So we square each of these statistics, each of them vertically, and then sum them up to calculate the eigenvalues for the first component, then in the same way for the second and the third one. So I'm going to show you how this can be done in SPSS, in Excel. I've already copied these values, these three columns, into this. So the first thing we need to do is to estimate the square value of each of those values. So square is, as you know, multiplying each number by itself. So this is going to be equal to this times itself, and you'll get this square valued. So the square of this is here. Now we need to sum it up, and in order to sum, I'm going to go to formulas under auto sum, and okay. So we got this statistic 3.301, and if you recall from the table above, the total, that's the initial eigenvalue, is 3.301. It's exactly the same. So by doing the same round of the type of analysis on the second and third column below, we can calculate 1.333 and can also retrieve 1.0.33. Let me quickly do that for you so you'll see what I mean. This one equals to this times itself, and all the way down. So our squared factor loadings have been estimated. These are squared factor loadings, and I'm going to sum them up. To sum, I just click sum and I'll get that. So 1.33, if you'll recall, and in the same way I'm going to do the same analysis. Equals this times this, enter, and I'm going to drag it down. So we have already estimated the squared component loadings or factor loadings, if you will. I'm going to sum them up to get the last eigenvalue that we need to estimate. It's 1.032, slightly different from the one we have. Actually, if I double click, it's exactly the same. It has been rounded up, 1.032, etc. So this is what eigenvalue is. We have been able to extract three components. The first one, so in this side we only have the summary of the important eigenvalues. We have the first component with 3.301 eigenvalues, and so on and so forth. And the first component explains 33.0 0.13% of the observed variance in the data. And that's what eigenvalue means, actually, the amount of variance that is explained in the data. So the amount of variance that is explained by the second component is 13.328. As you see that there is a sharp difference between the amount of variance explained by the first and the second one, and is most often is like that in both factor analysis and principal component analysis, with the first component or factor extracting the highest amount of variance. And finally, the last component here extracts only 10.33% of variance. Altogether, these three components explain 56.671% of the variance, which is pretty good. In some sources, you will see that scholars ask for anything above 50 or 60%. So I think we're getting closer to that threshold, which is not too bad. Now for Scree plot, we have the same thing. We have eigenvalues, which are plotted against the component number. So as you see, the highest eigenvalue here is the first one, which we saw above, I think it was 3.033, something like that. What was it? It was 3.301, and so on and so forth. One way of making sense of this is by, let me just draw this line. Around eigenvalue 1, you can draw a line and see how many, dots or eigenvalues fall to the right side of where this line and the line of eigenvalues intersect, right here. So here we see 1, 2, and 3. This is another visual way of finding out how many components are there in your data. And the number of components basically means that your items can be grouped into 3 components or 3 groups. Now for component metrics, it's the loading of your items on each of the components. This is not rotated, so I would suggest that you go down and quickly take a look at the pattern matrix. I prefer to look at pattern matrix over structure matrix because this is the rotated solution for us, and this is what we need to report in our papers or research reports. For example, item 1, which statistics makes me cry, loads highly on the first component but doesn't load that much on the third and the second and the third component. On the other hand, item 2, my friends will think I'm stupid for not being able to cope with SPSS, loads highly on a different component number 2, with a loading coefficient of 0.786. But the loading coefficients on component 1 and component 3 are not that high, so you can ignore that. The problem arises here when you're looking at component question number 3, which is standard deviations excite me, and it is loading negatively but highly on the first component and positively and highly on the second component. In other words, we have a kind of double loading or cross loading here, which is not very good news for us. One of the ways to take care of such solutions is that we can remove this item from the analysis and run the analysis again to see if we can get a better solution, because it's not clear at this moment. It's not clear whether this item is measuring the first component whatsoever it is or the second component. So a loading factor is greater than a loading coefficient, greater than 0.3 is necessary for us to assume that the item is measuring or is loading pretty well on that component. So you can go through the rest of the statistics and find out what item measures what. So I'm not going to go through the substantive meaning of these items and why they are loading on these components, because that will fall outside of the scope of this presentation. And well, you can just really skip structure metrics. Finally, you can take a look at the component correlation matrix, in which you find the correlation between the 3 components For example, one of the correlation between component 1 and component 2 is minus 0.180, etc. So the correlations are not that high, I should say. And here this is not too bad, but this is not that high, and this is not that high either. Now I'm going to quickly run another factor analysis this time round, and with principle, I'm going to keep this as is. Just let's get rid of the coefficients of correlation because that takes a lot of space. For extraction, I'm going to choose principal axis factoring. That's factor analysis. Okay, and then continue. And finally, for rotation, I'm going to keep this as is. And for options, I would like to sort my solutions this time around according to their size, and also suppress small coefficients so that those tables would be more reader friendly. So anything that is smaller than 0.3 will be removed, although it's basically still there, but it will not be displayed. So let's click OK. This is a factor analysis, let's remember that. So the determinant is the same, the KMO remains the same, and so does Bartlett's test of sphericity. What changes here is communalities. Like I said, the difference between factor analysis and principal component analysis is that in factor analysis you assume that the total variance is a function of common variance plus unique variance. And that's very obvious from the initial solution, in which column here you see it's smaller, way smaller than 1, whereas in principal component analysis everything was 1. So what we need to look at is this column. As you see, principal component analysis was able to extract a better solution for us because, for example, this item has a very low communality, and so does this. Therefore, if you compare the two, this is what I usually suggest, compare the two solutions, PCA and factor analysis, and to find which one returns a higher communality in the first place. So in this case, I think I will go with principal component analysis. Regardless, factor analysis is also suggesting that we should think about a 3-factor solution. However, in factor analysis, we just throw these away, right? And so the extraction sum of squared loadings under this column there would be a difference between the eigenvalues under this column and the eigenvalues under the initial solution. So this is what we need to take a look at. So in this solution, you'll see that eigenvalues in the second and third factor are basically not that high, and it's only the first factor that extracts about 23.3% of the variance with more than almost 3 eigenvalues. So I would like to retain only one factor here rather than 3, and it's this Scree plot just is a representation of the initial eigenvalues. So you can, in the same way, you can look at the factor matrix. This is the unrotated factor matrix. As you see, we've got empty cells, which, as I mentioned before, is because that we have required that SPSS eliminate any factor loading smaller than 0.3, and it's much easier to make sense of. Now, what we need to look at is this pattern matrix, in which the items have been arranged by their loading size, the size of the loading coefficient, and also those loading coefficients which are smaller than 0.3 are eliminated. So we have only one item which seems to be cross-loading, and that's standard deviation. Excites me. I think this is pretty much similar to what we got in principal component analysis. So this solution is not too bad either, but by communality, I would say principal component analysis was better. But I would say this is not still not too bad. Maybe one way of determining whether ultimately which one you should choose over the other one is to also compare the pattern matrices across the two solutions, across PCA and factor analysis. And last but not least is the correlation. It's very interesting to see that the correlation has improved here. This indicates that our correlations based on factor analysis is pretty larger than what principal component analysis estimated for us. So it seems that we have encountered a dilemma here, whereas the factor loadings seem to be better in a principal component analysis. The correlation metrics offers a better solution. Now, which one to choose is really something for us to explore. Tentatively, I would recommend that we go by the PCA results because the factor loadings were stronger and reliable. And after all, the factor correlation matrix was not totally useless. So this brings me to the end of this presentation. Thank you very much for your attention. If you like the video, please give it a like and stay tuned in. There will be more videos on other types of analysis. Have a good day.